Welcome everyone to our first lecture on Generating Functionology by Herbert Wilf. We're going to be talking about section 1.1. It's called an easy two-term recurrence. So first off, consider the recurrence. Let's say a sub n plus 1 equal to a sub n plus 1. So, you can generate some of this sequence, at least the beginning of it, and just say, well, we should probably specify that a sub 0 is equal to 0. So, the sequence looks like it starts with a 0. And if we put a 0 in, here, then we can see that the first term is actually going to be 1, okay? And then if we put that in, then we get 3, and continuing 7, let's see, 15, and 31. And, well, this continues. So our goal, So right now we have a nice recurrence relation, but the goal is going to be to find a closed form for this sequence. And by closed form, let's say for the sequence, a sub n. But by closed form, what I mean is we want to be able to explicitly write a sub n in terms of numbers, and maybe in terms of n. But the idea is we don't want it to be written in terms of the previous terms. We already have that. So we want to be able to come up with a closed form. And there's no reason that we would know what this would look like. We see that every term is being multiplied by 2, and that's what the recurrence relation tells us. So maybe we can assume that it's going to be 2 to the n or something along those lines, but we don't really know what it is. And this is where generating functions actually comes into play. So here's what we're going to do. We're going to take the recurrence relation that's given to us, and we're going to start manipulating it algebraically. The first thing that we're going to do is we're going to define a of x equal to, and this will seem sort of arbitrary at first, but you'll get used to it, some sum from n greater than or equal to 0 of a sub n x to the n. Now the a sub n is exactly the sequence that we're defining, the exact sequence that we've defined above, which is sort of interesting. Maybe this is the first time you've ever seen this, but what we're doing is we're creating an infinite polynomial where each of the coefficients are just elements of our sequence. And we would call this a power series. But for now, just define this to be our function a of x. And you can plug things in for x and actually get things out possibly. But really, that's not what we're doing. The weird thing is we don't really worry about convergence here. Most of you, if you're taking analysis or something, or even just calculus, you might be worried that a of x might not converge. But really, we're dealing with this formally. We don't really care if it converges. And honestly, a lot of the time, maybe you can see for yourself that if I put 1 in for x, it seems like it's just going to be my sum. It's just going to be a sub 0 plus a sub 1 plus a sub 2, and it'll just continue. So I can kind of almost view that like a sequence. It's almost like when I put in 1, it almost gives me the sequence right back out. And that's kind of nice. And maybe that's not exactly how we're going to use it, but you can see that this thing might be useful. And so what we're going to do is we're going to take the recurrence relation that's given to us, and we're going to try to make it look like this function, a of x. And how are we going to do that? Well, the first thing that I'm going to do, I see that we have a recurrence relation, so I'm just going to go ahead and multiply by x to the n on both sides. And n is just an integer here. So, first step. Multiply by x to the n on both sides of the recurrence relation. So we actually have a recurrence relation, right? Let's see. So what am I going to do? A n plus 1 x to the n, which is equal to, well, I'm going to distribute automatically. A sub n, or 2a sub n, x to the n plus, well, it's just x to the n. And what I'm going to do now is, step number 2, is sum over all n greater than or equal to 0. So I'm trying to make it really look like that sum, at least one of these. So if I just sum n greater than or equal to 0, n plus 1 to the n, similar. Let's just write it out. So the middle term, this one right here, is actually going to be just 2 times a of x. Our last term, this one over here, well, we can actually write that using our knowledge of geometric series. We could write this as 1 over 1 minus x. And again, some of you might be worried about convergence, but I just am throwing out a disclaimer. Don't worry about that at the moment. On the right-hand side, if I multiplied by x, then the n on the x here would actually match the n as a subscript. Right now they don't match, so the first thing I need to do is increase the exponent on the x by 1. And how I'm going to do that is I'm going to multiply by x, but also divide by x. I don't want to change the value of the expression, so this ends up being 1 over x times a over x, or a of x. And now, well, this is just an algebra problem. I can actually solve explicitly for a of x. I'm going to go to the next page here. So step number 3 is solve for a of x. And for us, well, let's go back. We're just going to add, or let's say subtract 2a of x to one side, factor it out, and then divide by what's left. And after simplifying, we actually end up getting a of x is just going to be equal to, and I trust that you guys would be able to do this, and after simplifying, we end up getting that a of x is equal to explicitly this. Now, I haven't motivated what we're doing, but the one thing that we do know is we originally wrote a of x as something else. A of x to us before was this long sum, and it didn't look super duper useful unless we put in 1, then maybe it looked like our sequence. But other than that, it was kind of useless. Now this looks like a function. And what's even cooler is this function is identically equal to that long series that we had before. And it has x's in it, so we can understand why this might be equal, but that's kind of interesting. And so what we're going to do is we're going to use our knowledge of, well, partial fraction decomposition, along with some power series techniques to see, well, am I able to figure out am I able to expand out what I know about a of x at the moment? Well, let's say 4, but use partial fraction decomposition. Use partial fraction decomposition. And the first thing that we're going to do is we're going to recognize that our function x1 minus x, well, first I'm just going to factor out an x. Nothing tricky yet. And now inside of here, I really want to be able to split this up using partial fraction decomposition, and you can work out the details, but it's not too bad. Recognize, well, this is something that, again, you'll have to work out the details for, but it's not too bad. We end up using partial fraction decomposition and splitting up this what used to be a product now is just a sum, well, in particular a difference, I guess. And we actually know what this looks like. Well, this is, again, we already used this formula before. This looks identical to the geometric series that we were using before. And so I'm going to keep this x outside of here. But the first piece just works out to be, well, 2 plus, well, let's just multiply the x in right away. And we end up getting that it's 2x plus 2 squared x squared plus 2 cubed x cubed plus dot dot dot. Okay, well, that's the first piece. And the second piece, again, it's just a simple geometric series, and I'm going to have to multiply the x in, which is why everything's increased, which is why we'll have powers that are, we don't have a 1, right? We don't have a constant term because we multiply the x in. But that's not the tricky part. The tricky part is recognizing that we're able to use the geometric series formula to just write it out as the power series. Simplifying this, well, if I combine like terms, if I combine the x and the x, well, I mean, I have to do 2 minus 1 of x, and then the second term, well, it's going to be, 2 squared. I'm just going to say 4 minus 1. Well, let's write it as 2 squared. 2 squared minus 1 x squared, and this continues. So, 2 cubed, and we're writing it like this because it's very suggestive. 2 cubed, dot, dot, dot. So now it's actually clear that, well, thus, the coefficient on x to the n, let's say, for some n would, well, I mean, the exponents on the 2 with the coefficient is matching the exponent on the x. So, well, the coefficient on x to the n is 2 to the n minus 1. Now, again, I haven't motivated what we're doing, but this is actually really neat because we just found a closed form for the sequence, for our original sequence. How did we do this? Well, we said originally, remember, a of x was originally equal to the sum, this sum, of a n x to the n, but we just determined, that it was also equal to n equals 0, n equals 0 to n minus 1 x to the n. Which means if we just relate the coefficients, thus we get that a sub n as a closed form is identically equal to 2 to the n minus 1. And that's the closed form. So this is how we use generating functions. Again, this is like the title of the section suggests. This is an easier one, but it's nice. And I think this is motivating enough to show you that generating functions can be very powerful. A generating function, again, I haven't actually defined what a generating function is, but this process that we just outlined, this is using a generating function. And in the next couple sections, they start defining what generating functions are, and we'll get into that. And we'll do some harder recurrences. So thank you for listening, and that concludes this section.